Hi everyone, I'm Jeremy, and today I'll be talking about my master's thesis, which was on MCMAS-Dynamic symbolic model checking for linear dynamic logic, or LDL, and several temporal and epistemic extensions. So, in August of 2012, the Curiosity rover landed on the surface of Mars. However, had things gone wrong, the cost would have been astronomical. So the rover itself was costed at about 2.5 billion US dollars. And thus, it was essential that any software loaded onto the rover was guaranteed to be correct and free of bugs. And so formal methods were thus used to ensure that this was the case, at least to the best of our ability. And so model checking was one of the techniques that was used. And it actually turned out that model checking did find a bug in the rover's file system. In general, formal methods often see application in industry, in cases where the cost of failure is very high, and thus it's essential to get things right the first time. So one specification language that's used in practice and industry is linear temporal logic, or LTL. So LTL is useful, but it does have limited expressive power. So we can use LTL to specify a safety property, like this one. If the engine fails, the train will stop in the next state. So this written as G, engine fails implies X stop, where G means that something is true in all future states on the path, including the current state, and X means that something is true in the next state. However, once we try and verify more complicated properties, we struggle a bit with LTL. For example, the train always has the blue flag raised in the even states. So the modalities LTL gives us allow us to say that something is true from here on out, as well as that something is true in the next state. So in particular, there's no real concept of parity, and we can try and emulate the concept of parity by using the next operator, but this leads to a formula of infinite size since there are infinitely many even numbers. Alternatively, we can use a trick called projective semantics, where we define a new variable, let's say q. We express what it means for something to be even using the LTL constructs. So that's q at g, q if and only if x not q. And then so q expresses what it means for a state to be even, so we can just say g, q implies blue flag. But this is difficult to do. In general, it works on an ad hoc basis. If we look at a more complicated spec like this one, so after the train signals to the controller, within one step it stops, then it alternates between trying to get entry and acknowledging the controller's response until a grant is received. This specification is somewhat more complex, and it's difficult to specify using the projective semantics, and the concept of alternation that we have here is not really possible with LTL. And thus this brings me to linear dynamic logic, which was the main logic that I studied as part of this project. So linear dynamic logic was introduced by Vardy and Giacomo in 2013. It is an expressive logic that supports all omega regular properties, so that's strictly more expressive than LTL. And it has a relatively simple syntax that's heavily inspired by propositional dynamic logic, or PDL. So an LDL formula, which is phi in our grammar here, can be an atomic proposition like P. We also support constructs from propositional logic, so that would include truth, the not and and operators, and also some abbreviations that I've left out here. So that would be like or implies. There's also a modality in this logic, so I'll focus on the diamond first. The intuition behind the diamond modality is that we have some prefix of the path we're examining that matches the path expression rho, after which phi is true. And the idea of the box is dual, so that means that after all possible prefixes of our current path that match the path expression rho, then phi is true. So the path expressions rho are specified over paths, as the name suggests, and they can specify that at the current head of the path, some LDL formula is true, so that's the test construct of phi question mark. It can specify that at the current head of the path, some specific propositional formula is true, which is psi. And we also support the standard construct from PDL, so that's choice, composition, and the clean star. So the main difference between the test for phi and the propositional formula psi is that if we test for phi, we are not advancing the path. If we test for psi, where psi must be propositional, then after we do this check, we are actually continuing on by examining the next state of the path. So going back to the properties we were looking at earlier, we can try and express them in LDL now. So firstly, the safety property. If the engine fails, the train will stop in the next state. So we can write this in LDL by considering that this is a global property, so we want it to be true after any possible evolution of the system. So we want to consider the state after any possible path, so that can be expressed by a box top star. So if the engine fails, then we want in the next state, so that's why we have the singular top in the diamond modality there. In the next state, the train will stop. Secondly, the train always has the blue flag raised in the even states. So this is much easier in LDL, because even states are states after any prefix of length 0 or length 2 or some other even length. And the concept of an even length can easily be expressed using path expressions as shown here. Finally, after the train signals to the controller, within one step it will stop. So again, this is a global safety kind of property, so we want it to be true after any possible evolution, hence box top star. But so when we have a signal, then within one step, so hence either in 0 states, top question mark, remembering that that a question mark does not advance our consideration of the path, or in one state, so just the top, it will stop, and then it will alternate between trying to get entry and acknowledging the controller's response. So again, this fits very naturally with the path expression try and then ACK repeated 0 or more times. And it will do this alternation until a grant is received. So yep, we get this, even this kind of complex specification can, without too much difficulty, be boiled down into an LDL formula. So if we look at the complexity, below checking of LDL is p-space complete, and this is the same as linear temporal logic, or LTL. So in some sense, we get the additional expressivity that LDL brings to us for free. Despite this, as far as we know, at that time at least, no practical algorithms, or for that matter, model checking toolkits for LDL existed. And so over the course of my project, I started by looking at algorithms for LTLK and CTL star K, implementing those as extensions of the MCMAS model checker. I then turned my attention to LDLK, and then developed a full branching time extension of that called CDL star K. And in the last part of my project, I looked at LDL K and CDL star K over finite traces, and it's interesting to see how the semantics as well as the verification changes as one moves from the infinite traces you examine in LDL or CDL star to the finite trace context. So now I'll discuss some of the details of the model checking algorithm I developed for LDL. So the model checking problem involves being given some system S and some property P, converting the system into a model and to some logical formula, and then checking if in the model that logical formula is satisfied or not. So for my algorithm for LDL, I'm using the formalism of interpreted systems, which is fairly commonly used to model multi-agent systems, and the specification language I'll be specifying properties in is LDL. And so I'll be using a series of transformations on both the interpreted system as well as the LDL formula to get it into a state where I can verify that the formula is true or prove it to be false and generate a counterexample. So as a preliminary, I will discuss the concept of alternating automata briefly. So these are very much like a non-deterministic finite state automata, except that instead of being in one state at a time, one can transition into multiple states at the same time, and the automaton is accepting if all the states one is in the current of all the states in the current set of states one is in are also accepting states. And based on these alternating automata, for an atomic proposition, the automaton we generate is pretty simple, because if P is true, we transition to an accepting state, otherwise we won't be accepting. And for negation, I didn't cover it here, but we can rewrite our LDL formula into negation normal form, and then for the negation of an atomic proposition, the automaton is just the reverse of the one for the standard atomic proposition. Moving on, for conjunction, what we want to do is we want to transition into automata for both subformulas of our conjunction. So this covers the propositional cases, but we still need to deal with the modal ones. And for this, we rely on the similarity between the LDL path expressions and regular expression from string processing. So we build mark epsilon NFAs for each of the path expressions that we have. And this is based on Thompson's construction from string processing, which is a relatively well-known algorithm for converting a regular expression to an epsilon NFA that recognizes its language. So this actually covers most of the path expressions, the exception being the test construct, which doesn't quite have an analog in regular expressions. So in 2015, Feynman and Zimmerman proposed the concept of a marking function, which is a mapping of states in epsilon and FA to tests. And this will come in useful later when we are trying to convert these epsilon and FAs into alternating automata. So they present an alternating construction, which is a recursive algorithm for constructing an alternating automaton for a given LDL modality, so either the diamond or the box, which recognizes precisely the paths on which said modality holds. So the propositional cases are handled as presented earlier when I was introducing alternating automata. So the construction has one limitation, that being that for the modal cases, it quantifies over all possible epsilon paths between nodes in the epsilon and FA. And this is a concern for practical algorithms because there can be cycles consisting purely of epsilon paths, and thus the number of epsilon paths between nodes and epsilon and FA may potentially be unbounded. And thus I introduce a novel notion of critical sets, which is a method for bounding the number of epsilon paths we need to consider. So given an LDL formula here, the intuition behind critical sets is we want to consider only the easiest for the diamond case or hardest for the box case kinds of paths. So in this case, the minimum sets of tests that we need to be able to pass for this automaton, so that's alpha or beta, and then beta or gamma, and then true, would either be just beta or both alpha and gamma. So in some sense, the only paths we need to consider are like 1, 3, 4, 5, 6, 8, 9, 10, or 1, 2, 4, 5, 7, 8, 9, 10. So a path like 1, 3, 4, 5, 7, 8, 9, 10, which requires us to pass both beta or gamma, is in some sense redundant, because if such a path would pass, then we can be certain that 1, 3, 4, 5, 6, 8, 9, 10 also would pass, and thus it's sufficient to consider only the easier path. And so based on this, considering only the minimal critical sets, which are the easier sets of tests, would yield the same transition relation for an instance of the diamond modality for the alternating automaton that one would obtain if one actually considered all of the epsilon paths. And I also show in the thesis that the dual case for maximal or harder sets and the box also holds. So we use all of these constructs we have so far to build an alternating automaton. So there's one thing we need to do, which is to remove the epsilon transitions, because these aren't allowed in alternating automata. And the standard notion of an epsilon closure does work, but there's one catch, that's we need to factor in the test labels. So let's suppose we want to transition from some state S to some state S double prime, and this is done by going through some set of epsilon paths to a state S prime, from which we can make a transition A to S double prime. So let's suppose also that the epsilon paths from S to S prime have some set of minimum critical sets, S1, S2, so on to Sm. So what we want to do is we want to pick some minimum critical set in which we are able to pass all of the tests that we need. So intuitively what we want to do is we want to disjunctively transition into automata for each minimum critical set that verifies that it is possible to pass that minimum critical set. And what we can do for this is we can build automata for each of the components of a minimum critical set, but we need to transition disjunctively into these, since we need to be able to pass all of the tests in some minimum critical set. So we now have a means of building an alternating automaton, and we now convert it into a form that's more suited for machine verification, that being converting it to a non-deterministic Buki automaton. Thankfully, this is a fairly standard algorithm called the Breakpoint Construction, which converts an alternating automaton into an equivalent non-deterministic Buki automaton that recognizes the same paths. So at this point, we build an automaton for the system, and that includes what our formula means, and then we run these automata in parallel. So there's one catch here, being that because our automata are built to identify accepting runs, as opposed to showing that all runs are good or bad, what we do is we build an automata for the negation of the formula instead. Because if we can find an execution where not phi is true, it means that phi is false, and because the semantics are that we want to check if a formula is true for all paths starting from a given state, this lets us say that phi is false starting from that state. And one problem we might run into here is that called state explosion, where the number of states in our system automaton increases exponentially as our system grows. And also for our formula, the size of the Buki automaton for our formula is exponential in the number of operators. So the model checking algorithm I just presented is the first practical LDL model checking algorithm to the best of our knowledge. It has a time complexity that's exponential in the size of the formula, but usefully it is fixed parameter tractable. We see that it's actually only linear in the size of the model, which tends to be larger. The algorithm was shown to be formally correct, and also amenable to a symbolic implementation, and this to some extent may help mitigate the state explosion problem that I mentioned, if one is dealing with large models or formulae. So as an extension, we consider epistemic modalities. So this allows us to express statements about knowledge. For example, using a prisoners and light bulb scenario, when the counter makes the announcement, he knows that everyone has been interrogated. So we use the standard observational semantics from S5, and we also support distributed and common knowledge. And we show that even when considering these, it is still the model checking problem is still p-space complete. So another extension considered was finite traces, and this is motivated by AI applications like planning, where traces might have finite length, and this might not be known beforehand to agents. And the method is based on reduction to an infinite trace LDLK model checking problem, although we transform the model and formulas accordingly to respect the finite traces, and intuitively this works by introducing a new agent that's able to control when the path is cut short. And it can be shown that based on the reduction I put forth in the thesis, and if you use a polynomial space LDLK algorithm, which exists because LDLK is itself p-space complete, then the finite trace problem is also p-space complete. So I'll now move on to discussing the implementation of these algorithms. So I implemented the algorithms as an extension of the MCMAS model checker, which is a state-of-the-art model checker for multi-agent systems. So all the algorithms were implemented symbolically, and we also added support for counterexample generation, which is useful for explaining, in some cases, why formulas are true or false, and several performance optimizations. So we verified a safety property for the prisoners and light bulb scenario. So that's when the counter makes an announcement, he knows everyone has been interrogated. And we see that for CTL star and CDL star, we are marginally slower than the base CTLK algorithm that MCMAS has. But to some extent, this is expected because CTL model checking is in P, while that for CTL star and CTL star is p-space complete. We also observe that the performance optimizations for CDL star are crucial to get it running quickly. As you can see, the unoptimized CDL star K algorithm fails very quickly. Okay, so in conclusion, over the course of this project, we developed, implemented, and evaluated symbolic algorithms for a variety of increasingly expressive temporal and epistemic logics. So this started with LTL, then went to CTL star, to LDL, to CDL star, and then to finite trace versions of the last two. So some possible extensions we could make to this project are as far as expressivity and functionality are concerned. We could consider a metric variant of CDL star, where we bound the length of a path prefix when considering a modality. And this can be useful for properties like liveness. And also we can look at parametric versions where we are trying to find the largest or smallest possible bounds that we can use for these modalities. It can also be interesting to look at a probabilistic variant, where because in real life very often with real hardware, there is a real possibility that hardware fails. For example, a bit in memory might flip. And thus to some extent, our current models work on achieving complete certainty as far as our formulae are concerned. And in some cases, it may be acceptable to have a small degree of error. Finally, this talk was given about 2 years ago, but I'm pleased to report that since then, there has been additional progress made. So my supervisor and I have released 3 publications that are based on the work done in this thesis. So 2 of these were presented at AMAS, and 1 was subsequently presented at IJCAI. And there's 1 more that's in progress as well. In terms of implementation, MCMAS 122 used to only support properties specified in CTLK or ATL. But I've been able to merge the support for LTLK and CTL star K that I've been working on into the mainline branch as part of this project. And I've also been in charge of releasing MCMAS v130 with the new features as well. The extension of MCMAS that I worked on that supports LDLK has also been released officially as an extension of MCMAS. So thank you very much for listening.